we got some great things going for us. The symmetry, the fact that every interimpartial sums to 0.
Hello, and thank you for watching my video. This is called Quadratic Polynomial Number Theorem, and it is a generalization of Euler's pentagonal number theorem, and we'll see what that means for known results, and we'll look at some new things too. And this is a submission to 3 Blue, 1 Brown's Summer of Math Exposition 1, SOME1. Thanks, Grant, this guy, and gang for inviting me.
Yeah, let me qualify that literal hand waving and state more clearly what I actually have just discovered on working through this video, and that is if we take an R with an attached Q is our quintiger primorial, except now we're going to divide it by 2Q, aka 1, 0, negative 1, so that we are getting the product of just the odd primes. The first two factors give us and positive 8, where 3 plus 5 equals then the length. And if we continue, let's do it this way. Okay, now we're just going to use our extension where we truncate the sequences. And then there are no more. So at R equals K equals 3, 5, 7, 11, 13, which gives us a sequence that is accurate up to the length, which is the sum of primes, of odd primes, as L of R of this sequence, the Q series. And because we did our trick here, this sequence is accurate up to here, and the length will be 3 plus 5 plus 7 plus it too will be symmetrical at this finite limit. It's just that we're missing, so there's another 13 out here that complete this symmetry. So we can first label our primes, and we know we get a negative 1 contribution from all of our primes. Yeah, let's give ourselves a little index here. 23, 24, 25, 26. So we'd be going up to get the full length of this finite partial product. In terms of a Mobius function, each of the primes obviously contributes negative 1. So when we see something like 19 with negative 2, well, we know there must be another combination of an odd number of distinct primes that sum to 19, and it can't be 1, so it's got to be 3. Let's use this for triples. 3 plus 5 plus 11. So it goes. So, and we can put some kind of a order to the possible combinations. So we can start, well, 3, there's nothing we can add lower that we can add to it, but 5, we can add 3 to it and get 3 plus 5, which we place under 8 because this is a partition of 8. And because it has 2 elements, it is a positive one. These combinations of distinct primes that sum to a given number, well, they're the partitions of that number into distinct odd primes. They also are exactly correspondent to the square-free numbers. If we were to instead multiply all of these combinations together, then we would have the entire set of square-free numbers and nothing but the set of square-free numbers, in each with a value of -1 or 1. There are no zeros when it comes to this sign value of a partition. All right, let's try it this way: 3, 5, 3, 7, 3 and 11 is 14.
3 and 13 is 16. So, and we can even then just go 11, 12, 13, 14, 15, 16, 3 plus 17, 18, 19.
Etc. like that.
5 plus 7, 5 plus 11 is 16. 5 plus 13 is 18. 14, 15, 16, 17, 5 plus 17, 18, 19, 5 plus
19, dot, 7 plus 11, 18. And you can see that we're getting that same, we're just going to have this same sequence with the same distribution, just, you know, a prime gap away, repeated, etc., like that. And so they carry on like that. But then, as we get into larger numbers and we've got more room for triplets, then we can see where they come in. 3 plus 5 is 8, plus 7 is 15. So 15, let's just start a 3 plus 5 plus 7. And like we did up here, so we are at a you know, a border, a juncture between this. Imagine these borders between singlets, doublets, triplets. So, and as that goes, these, you know, for whatever R we choose, we eventually run out and have a complete finite picture of everything up to that point. So, so triplets, and then you know, dot dot dot, and then there'll be quadruplets. First quadruplet is 8, 15, 26. And so that's way down here, and that's 3 plus 5 plus 7 plus 11. So we'll have, etc. like that. So the normal Mobius of n function, the sequence that it gives, is pretty slow. So if we were to look at the numbers that you get when these things are multiplied out, you're looking at, well, you got 3, 5, 7, 15, 21, 35, 33, 39, 55. These are just the, well, singles and doubles. We also need our 11. That's where our 13 is. Something like that. And so we very quickly are exhausted in terms of products that are less than or equal to 26. Because every factor is equivalent to 1 mod 2, this always alternates. Negative, 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 positive, 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 positive. Like that. Therefore, whenever we have a combination of a partition of n or of k into distinct odd primes, we're getting the full count up here. It's all constructive interference and not destructive interference. So the absolute values of these numbers give you the sequence of partitions into distinct odd parts. Then we know that the sum of the numbers in this sequence, and we can do You know, we could do a running sum, 1, 0, 0, negative 1, 0. Well, try it with a Sharpie, maybe I won't make a mistake. So 1, 1. 2, 0, 3. So that's our running sum. So that is the sum of not only these individual Mobius numbers, those are exhausted. So because each individual entry that we every one of them contributes either a plus or a minus in a given column, this number is the subsum of Mobius of n. We're just including them from future composites at an incredible rate. You know, and we're getting some really large numbers ending up coming in early on. Now imagine that we place a 2 in front of every one of these. We'll end up with something like 2 plus 3, 2 plus 5, 2 plus 7, etc. Except I'm already wrong because 2 plus 3 is 5. So let's put a 2 plus 3 here. So we're advancing 2 because we're adding 2 to every partition, and so this whole thing is advanced 2 places in one foul swoop. And not only that, because each partition now has an additional part above what it had before, its parity changes. Therefore, any list of multiple partitions into odd distinct primes, the total will just flip sign. The magnitude must stay the same, and the sign must change. We literally have the action of taking our sequence from the product of all odd primes and multiplying it by 2q. It's the same thing. All we're doing when we do that is taking this RQ primorial over 2q quintiger expression and multiplying it by 2q to recover RQ. Take a look at the sequence. It grows, and that growth right there is the numbers here. There's going to be just some pretty tight bounds from Euler on how high these can grow, and I think there might be lower bounds as well. And this is just the odds now. So when we multiply by 2, look what happens. Look what happens. If we have numbers up here, just like this section here, let's say, and we have a 2, negative 2, 2, negative 3, 3, negative 2, 3, ... When we negate, when we multiply this by negative 1, shift it over to, take a copy, multiply it by negative 1, shift it over 2, then we're getting negative 2, 2, negative 2, 3, negative 3, etc., like that. So, and because the sign is strictly alternating odd even here, these numbers are always then going to be of opposing sign, and so like we get 0 here, negative 1 here, 1 here, 1 here, 0 here. Okay, so we have this sequence 1, 0, 3, negative 2, 3. And we're just going to negate that and move it over 2, so we have negative 1, 0, 3, negative 3. So this is odd square free sum of Mobius, and underneath we have sum of even Mobius. Now these are subsums, and so are these. These are the subsums from the even square free integers, and these are the subsums from the odd square free integers. And because the sequences are essentially copies, the second one is essentially a copy magnitude-wise, 3, -2, so this should be 2, and then this should be -3. But we're in ... territory there anyway. Because these magnitudes and these magnitudes only differ by 2 places everywhere, and because there are upper and lower bounds available, and perhaps some improvements need to be made. Regardless, we're sketching a possible pathway to a proof here. So the idea is that that we're presuming, I guess, let's say that this sequence, because it's the same sequence in terms of magnitude, is ruled by some C1 log of some function of k. Let's say these values here are between these bounds. We presume is smooth. We're talking about asymptotic analytical functions here, well established in a range. This is going to diverge, although very slowly. So we can expect that as k goes to infinity, that because this is a number theoretic relation in integers, and so it's chunkier than that. We have the exceptions that are able to round the corner and move to another integer, so to speak. And there's no exact formula, so there's a variance. So we can actually just correct this and say that f of k equals f of k minus 2 plus some variance. So this variance is then a function of the relation of the asymptotics bounds, so this variance is relatively small. As tight as these bounds are, however you want to describe them as being tight, once you take the log, are going to be really tight because it's going to the values going to change so much slower. So we have these 2 bounds, which are already we're presuming are pretty darn good here, and then we are taking a negative of it and moving it over 2. So that these line up, and any 2 adjacent values are going to be pretty close to each other, which means that we're canceling everything but the variance. That this sequence, the final sequence we get for the full RQ primorial, with 2 included, is this 1, 0. I must have made a sign error here. Well, actually, so this sequence is the variance. Means this is like kind of actually incredible. This means that as this sequence and the copy of it goes by C log fk, the variance goes something like C log of f of k minus C log f of k minus 2, which is like 0. I mean, you can have tremendously large numbers here eventually. A log goes to infinity, a log goes to infinity, only so much slower. So the running sum of this sequence is the running sum of the Mobius function, only it's doing a lot of forecasting and getting all of the Mobius values, 1 or -1, for the square free numbers that are way ahead. Regardless, the point being is that if we have this kind of thing on Mobius mu, and we have to make adjustments for the fact that all the the folding in, and need a distribution proof to basically show that as this thing weaves itself together, there can't be a big pocket forming the size of the square root. We got some great things going for us. The symmetry, the fact that every interimpartial sums to 0, so we end up like almost being able to corner our exception into a middle pocket, and then just meet in the middle, where we realized in order to meet in the middle we'd have to pass each other, so it can't happen. And that's basically it. That if this is growing like log, then this is the variance and it's not growing, or it's growing extremely slow because it's log, and it'll never be able to accumulate from a zero. If we say there is some exception where sum of mu exceeds square root, the last zero before it pulls this off and has an exception above a threshold, that along here the variance there's just no way that it'll be able to get there, because it would take this long exponential and not simply a linear sum. And of course, the very first argument in the book on the truth of the agreement hypothesis says that the number of times odd square-free integers occur is more or less the same number of times that even square-free integers occur. And that's exactly what this shows. So, a sketch of a possible path to proving the Riemann hypothesis. I am grateful to the Summer of Math Exposition project and the idea of it, that here's a place where we can informally share mathematical teachings and information and research in a less formal environment without a bunch of poppycocking and hogwashing. And so I appreciate the opportunity to show what I've got going on. And that's it. Thank you very much for watching my video.